To prove this theorem, we need the following lemma. Let F, as before, be a field and let B be a block diagonal matrix of size n. So B is a matrix where all the entries are 0 except for on this quasi-diagonal where we get k blocks. Sometimes we'll denote this by the direct sum. B11 direct sum B22 plus all the way BKK. And B is assumed to be a matrix of size n where BII is a matrix of size n sub I over F for any I greater or equal to 1 less than or equal to k. And n sub i's summed up to be little n. The lemma says if B is diagonalizable, so I use this cute notation to denote diagonalizable. This is a square with a slash, and hope this is easy for you to understand. Then, so is B sub II for each I greater or equal to 1 less than or equal to k. Actually, the converse of this lemma is also true. If each B sub II is diagonalizable, then B is easily to be seen to be diagonalizable. But this would be the direction we need in the proof. The proof will be an induction on the number of diagonal blocks k. If k is equal to 1, then there's nothing to prove. And now we suppose as the induction hypothesis that the lemma is proved for k minus 1 or less. Direct summands of B sub ii's. Let the matrix C to be this block diagonal matrix B11 through B sub k minus 1, k minus 1. Namely, this is a direct sum of B11 through B sub k minus 1, k minus 1. And let little m be the sum of n sub 1 through n sub k minus 1. Since B is diagonalizable by our assumption, there exists an S that is non-singular such that S inverse BS is equal to this diagonal matrix. Now if you move this S to the right hand side, you get BS equal to S times this diagonal matrix Now, assume S has entries denoted S sub ij. Remember, S is an n by n matrix. Our next step is to try to utilize this block form of B, in particular this C and our induction hypothesis. To this end, we write S as this block form. There are two n blocks where C sub I is a column vector formed by the entries S sub 1i through S sub mi for I greater or equal to 1, less than or equal to n. And eta sub j is a column vector formed by the entries of S sub m plus 1 j through S sub nj for any j greater or equal to 1, less than or equal to n. It might look a little complicated for you to keep track of those notations. However, those C sub i's and eta sub j's are just the most natural blocks to form this 2 by n block matrix S. You can just think of this in the most natural way. That is precisely what we are doing here. Given these notations, as well as the fact that B can be written as this block matrix C BKK and the other entries are zeros, let us compare both sides of this equation in terms of C sub i's and eta sub j's. Now star becomes the following. So now you are replacing S with this block form. Now if you do the block matrix multiplication, this left hand side will be equal to this guy. And the right hand side becomes. Now, comparing both sides, what do you see? What we see from here is that C times cos I is equal to lambda I times cos I for any I greater or equal to 1, less than or equal to n. And B sub kk times cos j is equal to lambda sub j times cos j for any j greater or equal to 1, less than or equal to n. Now, our next step is try to show that both C and B sub kk are diagonalizable, and then we can apply our induction hypothesis on C to get the conclusion. since S is non-singular. This means that the rank of S is equal to n, the full rank. If you look at the submatrices formed by the first row and the second row of this block matrix, namely those two matrices, formed by column vectors Kc1 through Kcn and 8-1 through 8n, they will both have full ranks. The rank of the first guy will be equal to m, because m is less than or equal to n, and the rank of the second guy will be n sub k, because n sub k is less than or equal to n. What does this tell you? This tells you, by linear algebra, that there exists I sub 1 through I sub m, j sub 1 through j sub nk, such that Kc sub I1 through Kc sub Im are linearly independent, and 8 sub j1 through 8 sub jnk will also be linearly independent. And needless to say, over F, this is because if you look at the column spaces of this matrix and this matrix, they will have dimension m and dimension nk respectively. That is why you can find those subgroups of column vectors in here. Now it follows from this relation we just derived that you have this conjugation of C by this matrix formed by those linearly independent vectors is equal to this diagonal matrix. And similarly, this conjugation of B sub kk by this matrix formed by linearly independent vectors in here is also a diagonal matrix. Lambda sub j1 through lambda sub j sub nk. So we have proved that both C and B sub kk are diagonalizable, and in particular because C has only k-1 many diagonal blocks. And by our induction hypothesis, which says the lemma is proved for k-1 or less many diagonal blocks, we have that B sub ii is diagonal for I greater or equal to 1, less than or equal to k-1. This, together with the fact that B sub kk is also diagonalizable, just proved that we have the final conclusion of this lemma. So we are done with the proof of this lemma.